Okay, so I hate to break up very interesting conversations, but ones whose connections to the project are elusive, unless ID3 is going to take a very strange turn. Today we're going to be going over some furtherance of testing that I thought could be helpful for the teams at this development of their projects. I had witnessed, the growing investment in testing infrastructure, but I wanted to give some guidance as far as techniques to derive good test cases for projects. And we're going to be spending next probably 2 lectures, possibly a third, on this topic of using a principled set of methods to derive appropriate test cases that will positively, at least with a measure of thoroughness, test our code. Now, before I get started, I wanted to check if folks had received the email I would have sent through Moodle in the past day or so about the tutorial this afternoon.
I checked my email.
Okay, so something is off then at some point, because I requested an email be sent to the class through Moodle. Maybe there was a timeout or something, indicating that the tutorial, which today is assigned for student presentations, right, for presentation of ID3, that I'm going to have to, because I have a conflicting medical appointment which just came up in the past day, and which I really can't postpone for medical reasons, I'm going to have to postpone those presentations until Thursday class time. So Thursday at class, I'll anticipate reviewing your presentations. You have an extra day to work on them, or a little bit more than a day and a half. And hopefully you'll be able to use the tutorial time today to good effect. Perhaps it's to further refine those presentations. Perhaps it's to push on further with priorities for ID4. But I want to apologize. I'm not able to be here today. I've got to get across town, and we'll have to leave the review of the presentation until Thursday, okay? Yeah. Okay. So for the balance of the lecture, though, I want to talk about the issue of coverage tests. So when we think about approaching the testing of software systems, I have noted before that we're not talking about perfection. We're not talking, in almost all cases, about being able to exhaustively test all the correct up in the software under all possible conditions. Could you give me some reasons why? And why is that? Okay, so give me, so that's true. You don't know the conditions. That's a correct statement, although a somewhat abstract one. So can we make it more concrete? What don't you know? Yes.
How long it's going to take before you find the next bug, for instance?
Okay. So
there's no real way to know if your current coverage is perfect without further testing. That could turn out that way.
And that's generally the case. And why is that? Why is it that we can't simply cover it all? Do everything, have perfect coverage in the sense of testing our program under all possible conditions.
Well, when a string can't test it, no one uses it. Well, I mean, the thing is that we might just find that some people use it in an unconscious way. I mean, I haven't thought of that.
Yeah. Okay. So these are some reasons. Anyone else?
You can.
Can what?
I mean, in principle, you can.
Can do what?
You can cover everything.
Okay, that's a bold statement.
Well, I mean, we had this conversation before, but there's a whole Kyler, for example, that is completely tested.
Okay, so
it takes forever. It takes as much time to develop the test case, maybe more time to develop the test case than it does to develop the code itself. So it doesn't make sense for the bottom line to your project spending the time you have.
Okay, so I would say that your statement about there is a compiler which is provably correct using Coq is a statement. So how can we reconcile these things?
Well, sort of what you kind of touched on it, but generally speaking, when you have a bunch of people in a building working for you, you have to give one paycheck and you working for you, and sometimes you run out of those.
Indeed.
You need to figure out what the best use is there at the time.
Mm-hmm.
You can get more money.
Okay, so there's an issue of diminishing returns I'm hearing from Eric, and that's quite correct, that at some point it may no longer be cost effective to test. Early on it may be highly cost effective. Why might it be cost effective to test? You have to pay people. What's the benefit? Okay, so you get, and how does this, if we're to think along Eric's line of sort of the economics of the situation, how does that help your bottom line?
Well, I think you said before that the further along the project goes, the harder it is to fix certain bugs. So technically, you want to get all done right at the start to prevent bugs from becoming problems.
Yeah, particularly the bugs that are most expensive are those that are late, and particularly after deployment, particularly after the system is out there on people's smartphones. After the program is embedded and burnt into the firmware of the devices that International Road Dynamics has roadside worldwide, and which require an expensive update process to be conducted in order to update that firmware. So, if you're dealing with embedded systems that lay at the heart of many of our calls intelligence these days, or with apps that have been downloaded by users that are not continuously in contact, dealing with systems that need to be 24/7, with 6 nines reliability, it's very expensive to fix a bug with those, to install a patch, take the system down, inconvenience potentially a lot of people. It's going to take a lot of time. And in general, though, that's actually the kind of shorter term impact. The big numbers that you could have had, you won't be able because of this reputation for bugs. You had a system that's undershooting its potential, and those customers may go to competitors. Those customers may not buy this type of solution at all because you have given them reasons for confidence. So bugs cost. Bugs cost money. Fixing bugs often saves money to a point, but at some point it's no longer cost effective. But even so, in general, and this is a key word, it's in general, we cannot prove programs bug-free. If we can prove programs bug-free, what else could we do? For those who have taken languages in computability theory, or taken courses in computability theory, what would prove a program bug-free? We could actually solve what problem? Okay, we could solve a problem a lot harder than P equals MB turns out. The halting problem. We could figure out if an arbitrary program halts or not. If we could take a look at a program and say, does this program have a defect in it? Could it cause a divide by zero error? You could actually solve the halting problem by putting an arbitrary program in there, putting at the conclusion of that program a divide by zero error, and see, hey, is there a bug in this program or not? And use that in order to derive whether or not that program halts. Yes.
So in general you can, but can you?
In general you can.
Right.
But for certain subclasses of problems you can.
Can you build it? I mean, this is theoretical stuff. We're not in the range of actually doing this ever now, but can you build something that can do an arbitrary task, but that can be tested? Like, can you build it with the mind that I'm going to build it so I don't put any of those things in there that are hard to test, but I can do all the normal stuff?
Oh, I see what you're saying. So you're saying, could you, given a problem,
yeah,
could you create software to solve that problem in a way that's guaranteed to be exhaustively testable?
Like you could have,
in other words, guaranteed to be provably
like
correct.
You have a for loop that has an extra restriction that has like a default thing in the language that stops it from going above a certain number of times. Yes.
So the answer is the jury is out on that issue. I think what seems clear is that for a large class of practical problems, we could design them in ways, and perhaps using formalisms like languages, that would be amenable to formal proofs about their correctness. But we're not there yet. In your folks' professional lifetimes, we will be. And as Kurt indicated, we are living in a world now where there is provably correct sort of instances of some very large pieces of software, including compilers. Compilers which can be proven to adhere to a certain specification about the meaning of language constructs. This is a remarkable thing, given you could have, programs could be of any length. You could have a perfectly legitimate program in C, or in Java, or in Scala, or in Haskell, pick your language, which is awfully long, right? And yet, the fact that we can prove the compiler correctly translates that program into machine language for a given architecture is a remarkable achievement. And people are working on that very actively for operating systems. And with some operating systems, probably within the next 10 years, there'll be success in proving this operating system free of deadlocks, proving it free of kernel crashes, etc. That is a strong thing. But for the most part, and partly due to things pointed at by Eric, we don't have the option for our programs right now of proving their correctness under all possible inputs. There are many types of inputs with which our programs deal, as Connor alluded to, which are unbounded in their size. They're unbounded in their extent. Strings are an example. The timing of user input, the timing of their clicks, where they click. Even for very simple inputs, there's often a huge variety of possibilities. Think about an operating system shell, a console in Linux, and think about all the different commands that could be typed to that console. It's not possible to exhaustively examine every possible command sequence that can be typed into there within a finite time.
Would there be an infinite out combination of those commands?
Yes, there's an infinite combination. Now, what's remarkable in the compiler area is that you can prove that kind of the mechanism that handles any of those combinations will still be correct. And so you don't have to enumerate all of them exhaustively. You don't have to enumerate all possible strings to show that it's correct. But folks, we've here been giving a nod to future developments. Within your professional lifetimes, I do expect to see growing use of these formal methods to prove correctness. How many people in here are in 340 this year? Okay. I hear your election of that course. It's a very important course, I think, in the undergrad curriculum, and one which has inspired many a student for good reason. That course in other semesters has touched on some of these formal proof languages, most notably Coq. But this semester, I think you're dealing with Prolog and any other languages?
Yes.
Not yet. Okay. So in other semesters, they've dealt with Coq and shown how you could use that to construct automated proofs associated with program correctness. But this is not the reality of day software development yet. It will be increasingly so. Today, we're going to be talking about the very practical need to marshal our efforts, to prioritize our efforts, to systematically test our program so our testing at least pass the red face test, that at least passes muster in terms of basic coverage of testing. I mean, after all, you might not be able to claim for your program that you've exhaustively tested it. I would be, of course, most delighted if any were to demonstrate formally or with exhaustive testing the correctness of your deliverables for this class, but I don't think that's in the offing. But what you can do is not make yourself blush as I look over your tests. And what could cause you to blush? Give me a couple things that could cause you to blush if you don't have to be subject to blushing, but What could cause you to be embarrassed in terms of the gaping holes in your testing? What sort of gaps?
You don't cover certain functions.
Okay, you don't test certain functionality at all. Yeah. So, for example, you have this fine implementation of GeoSource, but you never test it online. You never test it without a network connection. Give me another example.
You test certain run cases, like Internet Explorer, for example.
Okay, yeah. So maybe you're using Selenium to do web testing against your system, and maybe you're using several different browsers to kind of test the correctness of how your web page is displayed, but you never consider IE as one of those. So that would be a gap. It would be a gap I could drive IE through.
Or, hypothetically,
yeah.
Somebody is doing all the tests from Windows and then on the dev for Linux, then
yeah.
it could be interesting side effects if some of the tests were designed to run on Windows.
Purely hypothetically. So moving right along. Fine case there, Eric. That's right. That would be a wee bit embarrassing. So those are some cases. In general, if your system has to be configured in different ways and different architectures, using different browser clients, if it hasn't been, if the functionality of your system hasn't been tested in terms of certain web pages, right? Even traveled to. If you haven't tested it with incorrect login information, if it's a gay site, you haven't seen how it responds if there's a login failure. These are all sort of obvious gaps. You haven't even basically, done any significant testing on whole areas of your system. And really, this lecture and the next, perhaps the one after that, will be about avoiding those big gaps. It's about avoiding just leaving yourself wide open, wide vulnerable to problems that you didn't catch in your testing. Because if your testing doesn't catch them problems, chances are the users will. Okay, so we're going to be discussing one approach to this, to wit, something called coverage testing. And coverage testing comes in many flavors. The simplest, the oldest, and the most widely used is something called state-based coverage. Here we're actually abstracting, through most of these types of approaches, our program either at a very high level of sort of black box test, where we're thinking about the different screen program can present, or different web pages, or maybe at the very detailed level of statements, we're abstracting it into a graph. A graph where you can transition from node to node to node by edges. These edges might represent sides of an if statement, or they might represent how you go from screen A to screen B based on a click on your Android system. And here we're testing the nodes of this. Not the transition between them, but instead the nodes themselves. Another focuses on those transitions. For example, in an if statement, which has only, it's not an if-else, but simply an if statement, it will try both the true case and false case. Try both ways and test that out, rather than simply saying, well, we try the case if it's true, and then we fall through, and so then we've reached all nodes, we've reached all statements. No, it tries both ways. And it turns out that there's successive levels of higher coverage. They're provably subsume each other, provably successively sort of more complete, more thorough. One of them that we'll be talking about is something called prime paths testing. There's also a form of logic-based testing called constraint-based coverage we'll be discussing. Now, some of you in this class will have applied with your own hands something called code coverage packages like Cobertura. These are packages which run your system through a set of tests and establish coverage tricks. And typically, vary from package to package which of those will be covered here. But the most common one is state-based test. It'll say the fraction of statements, or equivalently of basic blocks, not not quite equivalently, but very closely related, that are reached by your test sets. Okay. Now, this coverage testing can occur at either the black box level, for example, testing requirements. You're testing high-level design, or the glass box level. Okay, kind of where we know about the details of the implementation. Black box. Here, we're not paying attention to how it's implemented, but what it should do. Whereas the glass box level, we know all about how it's built, and we're testing accordingly. So here's a probably familiar at a certain level activity diagram for a common activity. What does this depict? Getting money from an ATM machine. Yeah. And you'll notice that it's mapped out in a graph-like fashion. So we have a set of actions or states associated with these nodes. Some are more states, like you're waiting as they're entering the PIN. Others are more actions, like you confiscated the card, in the sense it's a brief activity, or ejecting a card. You could think of them as brief-lived states. But we also have these branch points denoted by these diagrams. And what you'll notice is that we've sort of abstracted out all the vagaries of what this system looks like, and exactly through what motors it ejects the card or it confiscates it, exactly what the PIN entry looks like. We've abstracted that into a state diagram that's at a high level, so that we can reason thoroughly about what we've heard in our tests and enhance the thoroughness of that testing. So notice that it considers not only legal actions. This is very important. I think it has something to do with what Warren said there. Not only legal actions, these convenient actions we as software developers typically consider. You know, where you go, you enter your card, and it prompts for the PIN, you enter it, and it checks the PIN, and it prompts for the transaction, and you select the account, and you request the cash, and it prints the receipt, etc. But it also considers these other cases, which are inconvenient for software engineers to consider, but very, very important. Cases where there's error conditions. Give me error conditions that happen.
Well, like I'm thinking about ETN in hospital, you can see the card out.
Sorry?
Card out
during it. Okay, yeah. So that's a good one. And in fact, I don't see something that sort of indicates that for any of these states, if the card is removed, it should abort. It should go to a state which indicates an error. But that's a great example. There are other cases here where the card is not recognized. Have you ever tried to enter, put a different card in there and see what?
Oh, it's more like I've tried to put my ATM card into my room card computer sometimes.
Oh yeah, no, that can happen. How many people here have ever had the card confiscated? I've had that happen. I remember it happened about 24 years ago or something. And I didn't. I mean, believe me, I wasn't like bankrupt or something. It just took the card because I think unbeknownst to me the card had expired, so it sucked it in and that was it. I wish I didn't go in, because then I wanted to get the card replaced. I didn't even have its number anymore. It just sucked it in and it said you have to go get a new card or something like that, which was a most ungracious way for it to behave. But the point is here that we're considering these various cases. And, if we're going to think about building a similar diagram for your software, we're going to need to think about similar cases where the user does something inappropriate. We have to be able to handle that and hopefully handle it gracefully. And at the least, we want to test, how does our system behave? Because if you don't test it, someone else in this room might, right? And someone else not in this room, most importantly, your users might want to do that. So here, you're going to want to have these cases of that are inconvenient, that are perhaps not typical, that we often brush under the rug, but to successful delivery of this system. After all, if you didn't handle errors, you might allow any PIN to be entered and to suck out money as a result. You wouldn't long stay in business. So here we have a state diagram that's abstracted. This is another one. This one is a little dated now for tickets, but for some destinations, this still occurs. Okay, so you make a reservation and you claim you're going to be proceeding to payment, but it expires. So you leave that orbit site for too long, it's sitting there, and the flight is canceled to restart. I don't know if anyone has been in that situation recently, but it happens very quickly on these sites. They don't want to grab seats and retain them for a long time. Or you pay for it, and you cancel it to request a refund, or you get it ticketed and actually it's physically given to. This could occur for airlines. This could occur for other events, for example. But here, we have an abstraction of the system into these pieces, and we can reason about coverage. We can reason that our tests are covering certain scenarios going through this system, but perhaps not others. For example, a case where you've paid but requested a refund. And by mapping these things out, we can spot these gaps within our system. What we're going to be talking about is mapping these out so we can thoroughly enumerate a set of cases that will be guaranteed to cover at least a certain level of reach within the set of test cases. This is another example associated with maintenance for some piece of electronic hardware that might be used commercially, and what's the process for sort of requesting maintenance. We'll be coming back to some of these examples. Those are all at a very high level. These depict processes associated with purchasing or with maintenance, and processes associated with extracting funds. By contrast to this, we can also abstract our program at a lower level. Here, dealing not with it in a black box sort of way, what it's supposed to do, but with actually how it's implemented, dealing with the details of its implementation in terms of key pieces of code, perhaps certain algorithms that are particularly. And here, we can turn a bit of code that you see here in a C-like language, C family language. It could be Java, C++, Objective-C, C itself, etc. And you abstract it into a flow diagram. So a while loop is rendered as on the right here, and an if statement here on the left. And once again, we have an abstraction. We have something that hides certain details, like the vagaries of semicolons and exact textually arranged and all that sort of stuff, but it brings out the essential features of the situation, the flow of possible control and the conditions under which certain control flows one way or the other. These components are associated with a node or what's called a basic block. Has anyone here taken the compiler course? It's not this year, but next year it will be. So it would be a precocious student indeed who had taken it already. But I would recommend it to you for the rigor of its coverage and the substance of its content and the implications for software engineering. Building a compiler for many decades, it was a foremost challenge of software engineering. And there's some beautiful software decomposition techniques that were honed in the area of compiler design and construction that have lessons across software engineering. Very nice, elegant solutions to a devilishly complex problem. A problem so complex that it's depicted using what sort of beast from cryptozoology? What is the moniker of the dragon that adorns the book of the most famous, the cover of the most famous book in that area? What does it show? It lies not there. There's not a griffin, not a chimera, but a dragon. And I'm tempted to render upon this board, but I'll leave it to your imagination. The dragon, but actually it's shown as a dragon because it was considered so devilishly complex. People didn't know how to approach it for a long time and struggled through it. And now it's a combination of art and science that's reduced it to a manageable software engineering challenge with intriguing theoretic and practical interwoven issues. Okay, so this whole coverage enterprise, how are we going to go about pursuing it? Well, this lies before you a slide which many a student would have wished could be available to them on exam. Because I often ask about exactly these questions. What are the main steps associated with coverage procedure? So we enumerate them to you, and then we will see how they're applied in a number of cases over the course of the next few lectures. So the first thing is, we identify the set of things that we wish to cover. Now, that's a very abstract statement, and what I mean by that, let's be specific. I mean that you want to cover the statements in your program, or you want to cover the transitions between web pages, or you want to cover the button press events, or you want to cover the prime paths in this algorithm. So we identify some set of things we want to cover in our testing. The idea is we want to set tests which will allow us to thoroughly cover, so guaranteed to have covered at least one of each of these things, at least each of them at least one. Then, we want to develop a set of abstract scenarios. These are most traditionally paths that include all the things we need to cover. So these will typically, ladies and gentlemen, be paths from start, and Lewis Carroll said it, first to finish. And we then, having identified those paths through the system that will cover these things, we then need to make it concrete. We need to turn those abstract paths, the things that will go this way in the path, we need to create cases for each of those paths that will exercise that path, that will make that happen. And that is often an exercise in ingenuity, because you got to figure, how could we make it go first this way and that way, for example? So here we're coming up with concrete test cases that will exercise. And what is associated with a concrete test case? If I say to you, I want you to run this, what is the key thing I need to specify for you? So you have a program and I say, I want you to run this test. What is it I'm giving you? The what to your program? The input. Thank you. That is exactly right. It's the input to your program. So each of these test cases will be associated with some specified input. It will say, run this under the input. And by listing those out, one after the other in the test, you're going to be able to then exercise these abstract paths through the program. Ones will go this way, we'll go from this screen to that screen to that screen, or we'll use this functionality and then this one and then that one, or we'll reach this set of statements, that one, we'll go this way through the while and then that way through this if or what have you, in a way that will guarantee this coverage, that we've reached each transition or that we've reached each basic block, that set of things we identified at first. Okay? So here, we're typically reasoning about the sort of ways we could test it from start to finish. We want a complete test case that will exercise the program. And mind you, in these set of test cases, some of these things we want to cover may be covered many times. The statement at the beginning of the program may be covered every test case. That's fine. That's fine. It's not a problem. As long as we've tested it once. Okay? So let's give a little example, make it a little bit more concrete, and as I am wont, I'm engaging you in a bit of spiral learning here. So we're going to sort of come around to get more details about how we do this. I want to build up the ambition. So here lies before us a program written in the language C, and this program translates a string from CGI encoding, type of encoding commonly used with HTTP, to plain text. So in this context, pluses turn into what? What does a plus mean in a query string? It translates into a... Well, okay, so it does indicate concatenation in certain languages, but in this case, this is a string like we'd type in a URL. And what does a plus indicate if it's in a query string? I don't know how many people here have taken 350? 350? Going once? Going twice? Okay. Two. What does a plus turn into? It turns into a space. Yeah, in fact, it does that. Okay, and then percent sign. And, percent sign 3F, what does that turn into? It would be a special character as encoded in ASCII by a certain hex value. Okay, and so basically what this is going to be doing is it's going to be taking that URL and turning it into a string that will translate presumably into a path request for the server. So right when we write URLs, we can't write certain special characters in them directly because those characters mean something different. And so we encode special characters like a space using other mechanisms like plus. Does that make sense? Okay, so that's the purpose of this program, and it's the purpose of this algorithm, and it sits before you, written out in C. And we can turn something like that by dividing it up into basic blocks into these chunks. Each of these basic blocks, ladies and gentlemen, when I say basic block, what do I mean by that? What I mean by that, it's a term from compilers, and refers to a set of statements. If one of them executes, they're all executing. There's no branch between them. They're kind of a linear sequence of statements. They go one after the other. So if the first is reached, the others will be reached, okay? So here's a description of that same algorithm here. You notice we'll have, for example, this if statement. So we're looping through this. Oh gosh, I hope you folks have further acquainted yourself with pointers. So we have this pointer to the string to be decoded to this URL, and for each character in the pointer, we're going through, we're getting that character, calling it C, and testing if it's plus. If so, we'll handle it. We'll append a space to the thing that we're creating. If it's to this buffer into which we're putting the decoded string. If it's a %sign, then we've got to go figure out the digits, the hexadecimal digits, and turn it into a character according to ASCII encoding, which is what's done here in this block here. So here we have these various if statements, all within a while statement, and that turns in, ladies and gentlemen, to this. So we have while going here, this sort of big loop back to the top of the while to iterate through each character in turn of the input, okay? And for each of those characters, we are determining if it's one of these special characters like plus. If so, we handle the plus case. This should be a space. There's a space there between those things. If it's false, we see if it's a dollar sign. This is actually it shows the two levels of branching. It's an if else if else in the original code, and we have these blocks, each associated with these bits of code. So we've taken that code and we've imposed upon it a control flow graph that shows the various ways to which it could branch. Are people comfortable with this? Okay. I was probably working with these things before you were a speck in the cosmic, so I lose track of how natural these things are to me. A physicist once told me, I had the privilege of working alongside a physicist between my undergrad and graduate school, and we were working with some descriptions of differential equations, and at one point, this physicist I was working with, he did a thing with the model. I didn't know what he was doing, but he transformed it in some way. And I said, "What are you doing there?" He said, "Oh, we're non-dimensionalizing it." I said, "What?" He said, "This is what physicists." He said, "To a physicist, this is as basic a reflex as sucking." We like always do this. We just have an impulse to non-dimensionalize things. And I said, "Oh, okay. I guess I lack that impulse." But are people comfortable with this idea of taking those blocks of code and putting them into kind of a flow graph like this? These are the basic blocks. If you reach the first one, you'll just fall through to the later ones, and then there's a branch, and by definition, that's occurring at the end of the basic block. All executes together. So here we go down, and then we either go this way or this way. It's just the same algorithm written in this different form that brings out the network structure. Okay with that? Does anyone want me to talk more about that? Okay. Let's talk now about. Okay, so if we have this, then we need to reason about. Okay, suppose now we want to test statement coverage for this code. What would we need to cover here? What things would we need to cover?
We covered basic characters. What we put in the string, we cover plus input.
Okay.
We cover.
Okay. So Warren, as his wont, is 2 steps ahead. But I was trying to motivate even a more basic question. But on this, if I looked at this picture, what sort of things if I talk about statement testing, what sort of things will I need to cover here within this picture? Every single node, A, B, C, D, E. At least one time, I need a test case that will go hit A, right? Now, that one's pretty easy. What's going to be more tricky, and this is where Warren was going, is, for example, I need one that's going to hit I here, or going to hit F, okay? So the first thing is, so to break this down into pieces, I'm going to delineate paths through this system that will cover the nodes. So give me a set of paths that will collectively cover these nodes. Give me one path to start with. Okay, but I need to, as Lewis Carroll said, you start at the beginning, you go to the end, and stop. So let's start at the beginning. Where's the beginning here? Okay, good. Good. So it's with A. Great. Good start. At 2 levels. And so we here have A. It stands before us. And then we're going to need to start at the beginning, go to the end, and stop. So Lewis Carroll may not. I'm planning on unpacking that into C, but the principle carries over. So you go A, B, and then, well, pick your poison. I mean, you can go to false to M here, and you stop to return, right? Okay, so that's one path you could take, right? Another path would be what? Enumerate to me a path that will end up with a return statement. A, B, okay. Okay. Yeah. L. Okay, B, yeah, and then M. Good. Now, are those 2 paths collectively covering all the nodes? No. Okay, so what else might we need a path to cover? Give me another one that will further our progress towards coverage of the statements.
You can do a while loop. You can do them all at a single time. Every time you go through the while loop.
Okay, and that's a perfectly fine option. Could you have a while loop? Riddle me this. Taking inspiration from taking Krugerian inspiration, could a while loop that would cover in a single path all of these nodes?
No, I mean you already have a while loop. So
okay, but you have a single path that would before returning cover all the nodes. Yeah. And in this program, you could have it go successfully up, and that was the Krugerian insight. But in general, that's always true. For example, there may be an error condition, right? And you either have that error or you don't for this particular.
One of 2 conditions, like an or
yeah.
Or this, then if the conditions are fulfilled, the mouse not have a chance to fulfill the other one.
Exactly. Yeah, exactly. So you'll notice actually is an error case. In fact, here. There is an error case here with have an incorrectly encoded hex value, but then it can continue on. So in principle, we could do a single path through path through this code could in fact cover all, but in general that's not the case. Or we could have many paths, right? We could have one, but however you want to decompose it, you can identify a path that you want it to hit, and then guess what, folks? You have to turn each of them into strings that will exercise that path. For example, this enumerates a set of test cases, and I apologize for the small font here, but a set of test cases that will exercise all of these paths collectively. Each of these test cases, whether it consists of just one string or several strings, will, taken collectively, those test cases will in fact cover of these. Okay, so this last one is exactly what was suggested earlier. It's a single path. It's a test case which will exercise that path through the program, a single path through the program from start to finish, which will in fact hit all these blocks. But this first one consists of 3 strings. Some later ones consist of 4, which will also collectively exercise those paths. That much is up to you to choose. But if we want to stand here with a straight face and say that this code works, confident, that there's no null pointer exception, that it won't, that it operates and handles all the cases given to it. To develop real confidence in that, you'd want to have all these different cases. After all, each of them is put in there, each of these if statements is put in there for a reason, and we'd like to be confident that handles those cases that motivate that reason for that logic. So here, test cases will exercise these paths that will cover all statements. So that's good. That's good. I appreciate people's engagement with this example, and you'll find that there's a lot of latitude here. There's nothing that tells you one of these test cases is inherently better, given that you're trying to cover all statements here. But each of them at least has base plausibility in terms of saying, I have reached all that code. And when you have tools such as Cobertura that try to test coverage of your program, traditionally most of them have operated at this level of sort of taking coverage at the node level of your program. Okay. Now let's suppose that we exercise that test cases. What would we need to do? So suppose we were to feed in the first of these, or perhaps the Krugerian fourth of them. What would we need to do? So we feed that in. How do we have confidence that the program is operating correctly? So we feed in that test case. Suck it into there. What do we have to look at? Okay. The value of OK that's returned. Good. What else do we need to look at? The decoded string, to see if this actually yielded a decoded string that was appropriate for this, right? Because this encodes, this string in T4, the single string, for example, encodes some string. It encodes some normal string, and we'd want to make sure that normal string came out. Good. And we want to make sure that it doesn't yield seg faults or bus errors or null pointer exceptions or fill in the blank for your 214 griefs, in the process of this, right? Right? Okay. So here, these test cases could give us some comfort if they've operated correctly, if they've yielded the correct output in terms of OK, output in terms of the decoded string as written to this decoded buffer, output in terms of that the program halts successfully, it finishes, that it doesn't crash. There was some confidence that the program is not terribly messed up. Does it guarantee correctness? Are we sure the program is correct if it passes all those tests? No. Okay. Yeah, there's certain testing we haven't done. We haven't done certain tests. We may have tested G, but we haven't made sure that G works. For example, when G is not the best example, but for example, give me a better one. We may have tested, for example, in our code, and I'm checking here right. We may have tested F, but we haven't perhaps tested it under a scenario where G occurred earlier and then it reaches F, for example. And that might have left some pointer off or what have you in a way that F would then malfunction, whereas if you just executed F, straight line path from A, B, C, D, F, L, maybe then it would work fine, but if it had gone first through G, maybe G would have fouled things up, so if it reached F later in the same path, it would have caused problems. So that might not have been revealed through perhaps the first test suite up there, but might have been revealed through the second. So in short, these test cases, these concrete test cases that I was talking about when I was talking about the sort of stages, okay, that's interesting. These concrete test cases, these things don't guarantee correctness, but they can at least prevent wide open vulnerabilities, right? Decrease the likelihood something gross will be defined. Okay, so why do we do this? Why do we build these models? Well, it provides several levels of benefit. Once we can document our test cases, we can reason about coverage and non-coverage of our test cases, about the risks of not testing certain cases. We can communicate those things, and we can use them to genuinely derive test cases. Now, in some cases, by creating these flow graph models, we can automatically derive test cases against model specification. So let's talk about these sort of things. I'm going to skip forward a bit. Key to all of this section, all of this is going from something like this to sort of graph we saw earlier, going from something like this, a description of the maintenance process, to something like this, where you break it up into these functional pieces in a familiar way. We're hiding details here, but we're not breaking up certain types of details, but we're capturing some key elements that allow us to then reason about its behavior. Or mapping this specification for how you process an order into these kind of pieces. I'm showing it in different ways, but all of these are examples of abstraction. We talk about abstraction as testing, as sort of hiding details. Turns out there's many details that we're often hiding for simplicity. For example, we'll see history-dependent states come up. A state which can only be invoked based on earlier states that were reached. Or we may omit sort of a very large state space and very much simplify sort of the set of possibilities. Or we may omit error transitions. For example, the one mentioned earlier by Warren, where you can yank your code out while it's in the machine, or ones that are perceived as impossible. We need to be aware that we've sort of we haven't noted certain, we haven't captured some things. Okay, so I'd like to talk now about successive levels of coverage. And we're going to be working up on this the next few lectures. So it turns out that having defined this notion of coverage, in particular types of coverage, such as path coverage, coverage associated with these graphs and code paths through them, we find successively higher, more rigorous, more thorough levels of testing, okay? And a subsumption hierarchy is shown. When I use this word subsumption, what I'm talking about is that down at the bottom of the hierarchy, we may have types of coverage that are shown, that are very basic, successively higher levels that are ancestors of that within this tree that's shown here, within this DAG that's shown here, include everything that's tested at a lower level, but have extra thoroughness of testing. So, for example, here, edge coverage includes node coverage as a subset. So, if you have covered all edges of a given diagram, perhaps this diagram here, this diagram here, this one here, you have, by necessity, covered all the nodes as well. But the reverse is not true. If you've covered the nodes, you haven't necessarily covered the edges. Does that make sense? If we assume it's a connected graph and there's a link between A and B, if you covered this you must have reached, in other words, you transition at least once from A to B. You must have been in A and you must have been in B. And it turns out that we can reason successfully higher levels. Edge pair coverage, sort of which pair of edges you came from and you left by out of a node, that can be reasoned about, that you've covered all possible combinations you came from. So you have perhaps a node where you have something like this, A, B, C here in the center, D and E. You could have come to C from A and left D. You could have come to C from B and left via E, or you could have come to C from A and left via D here, or left via E, for example. So all possible combinations of kind of where you came from, where you left to from a given node could be considered. We're going to be talking about prime path coverage, either next time or the time beyond. And then finally, there's complete path coverage, which is typically untenable. Why is it untenable to have complete path coverage? Cover all possible paths through this program. Yeah, way too many paths. You can go through perhaps this while loop arbitrarily many times, maybe getting user input, read, eval, print loop, REPL loop, and you can't possibly test every possible iteration of it exhaustively. There may be logic testing types of approaches, like with clock, that could reason about successiveness, but it's not going to be by simple enumeration. So the further up we go in this hierarchy, ladies and gentlemen, the more complete, the more thorough, the more time-consuming, and often the more complex it is to derive these things. Okay? Okay, more information they'll often require. And you'll notice that not all these things are strictly in a tree-like hierarchy. Okay, so we're going to be talking about state coverage now. This is the most basic sort of form. And here, for this high-level graph, and please, ladies and gentlemen, I'm not giving these lectures simply for fun, although there's an element of that. I give them not out of simple intellectual excitement, although I don't deny that. But I give them because I think that they'll be useful to you at least at basic level. So, with your programs, you could, even now for the undergrad teams, should be able to diagnose kind of the functional states the programs can be in. Or perhaps there's the user interface states. You should be able to create for me a graph where the transitions represent things like clicks, button clicks, clicks on URLs, frubbing of drop-downs, error conditions, or what have you. You should be able to draw that out in a directed graph. And you should be able to construct a set of test cases that at least hit every node here, right? And if you haven't, I may do it for you. And things may get discovered, as they often happen. Too many student projects I've seen, the first time you go to a certain place in the system, and something weird happens. And I don't want you to have that happen with me. I'd like you to guarantee it before. So, please, ID 4, a graph of your program. This is a foremost request. ID 4, I want to see this. I want to see a graph in this form of your program that shows some abstraction. I mean, you can pick exactly how you do it, whether it's UI states or functional state in terms of kind of the state of the system in terms of its logic that it's in. I'm not going to be really particular. I want to see transitions between them, and I want to see some discussion of how those tests relate to them. Okay, so here's state coverage. This is the most basic type. You hit all the nodes there. Hit all the nodes. You go at least once to every screen of the app. What could be kind of more basic, right? This is the simplest, and it's the weakest type. It's great. It's a lot better than no coverage of that. It's just incomparably better, but it's still fairly weak. Where are the testing gaps here? What's not being covered? Transitions, yeah. So this here, in this case, we may have explored the system through the UI, But if we've never really tested it with this refund being requested, it's still pretty weak. We haven't really put it through all its paces. Similarly for this case, maybe where you canceled the ticket, you've requested a refund through this. Maybe you've only done this give ticket case. Man, you haven't tested either of these cases where you're requesting refunds using the state coverage. But heck, it's a lot better than not reaching any of these states. Never a state, you do have this cancel case here, but never a refund case that you've requested. But at least you've tried canceling, right? But you haven't actually verified the refund mechanism works. So here the paths taken reach each node on the graph at least once. There are testing gaps, but it's better than nothing. And there's a common vulnerability with this. The code works fine based on one path through the code, but fails on a different path. You can easily imagine cases, for example, where a given block in your code works fine for one path to it, but not based on another path of the code. Maybe there's a null reference exception in Java, or maybe you didn't have a file handle properly opened if you fell through this loop and through this if statement in a certain way, and as a result, the code will fail. This is a sort of failure you can get in a language like C. So here, we assign a null value to some variable, and then later there's an if statement, and you assign a newly allocated value to that variable, and then you assign through that reference, and guess what? Maybe you think, based on some reasoning, that this later statement, assigning through the pointer p head, will never be reached under cases where p head is null, but maybe your analysis is wrong. Maybe you misunderstood something, and you do end up reaching this, and it causes a null pointer exception. Quite possible due to faulty reasoning. So the next level up from this is edge testing. And here we're exercising all transitions at least once. I think I told you, I remember person in the next office to me on the Microsoft Excel team really sweating over what's probably the core algorithm of Excel to redo dependency, recalculate the spreadsheet when some data changes. And what he was doing was edge-based testing. He was testing all possible transitions within that code, making sure it reached at least once, every transition at least once in the test cases. And it was painstaking work, very careful work, but very important work. So, here, once again, many test paths may cover a particular edge. That's no problem. But we want it to get covered at least once. Okay? Now, we're again reasoning, remember, from start to finish. We want to find these test cases that will start out, their inputs will take us from the start of the algorithm to the end of it, the start of the system to the end of it. They're a complete kind of use case, as it were, even though it may be at the code level. So for each path, we have to find a specific situation that will exercise that path. Do you remember that earlier? Do you remember that? Speak as in one voice. Okay. Thank you. Do you remember this? It wasn't half an hour ago I stood before you, and remember we were talking about paths like A, B, C, D, F, L, M. Remember that? And we had to unpack it into a case. We had to sort of, think hard about, okay, what particular case is going to get this thing to go to the false side here? Well, okay, we can't have a plus here. Or what would make it go from C to D to G? Okay, we got to have we can't have a plus. We have to have a percent sign here, and then it will get over here to G. So we have to really think to arrive at these test cases up here. Yes, Alex. Okay, if you put percent Z. Well, great question. So, ladies and gentlemen, as if in a Greek chorus, characterize for me the flow if you had percent at the start of your sing. A, B, C, D. Okay, this G, right? okay, percent Z. So it's actually not going to be a legal hex value, so it's, be H. Sorry, it's actually I, because it's equals -1. So it's indicating it's an illegal hex value, Z, so it's going to go to I here. OK equals 1 equals, oh, don't get me going on that. That name is horrible. Horrible. Yes, and I talk about passing the red face test. I feel perhaps a blush coming on to be presenting this code. So, ladies and gentlemen, I present this code to you as bad naming conventions. So it's at least it's not X. Okay, OK equals 1. That's sort of the Unix convention for returning 1 if it's, or non-zero value if it's bad. Okay, so you go to I, and then what? Then L, and if that's the end of the string, what happens then? M. So ladies and gentlemen, if we wanted to have all edge transitions here, what will we need to cover? Well, in this case, is it anything more than what we did with state transitions? Every state has exactly one input. No, that's not true. L, for example, has many inputs here, right? L has many inputs. In this case, I think it's the same as node coverage. Among other things, this is not going to require any cases where we, in other words, in order to get to F, there's only one way to get to F from, for example, D. So next time we'll see some cases where they are different, and in fact I've diagrammed one out here in my closing example right here, where node coverage is different than edge coverage. Node coverage here would involve what? Can anyone say? Node coverage here would involve N0, N1, and N2. Edge coverage would involve what? Taking both. So N0, N1, N2 would not be enough for edge coverage because you'd also need to take what? 0 to N2, right? That would be enough now for edge coverage, which is a superset. In this previous diagram, if anyone could find this, if anyone could find a violation, a difference between edge coverage and node coverage, I could give some extra credit. So you're welcome to suggest it. I haven't pondered this, but glancing at it, it's not obvious to me that there is one. Okay, so that's all for today. And again, tutorials are up for you today. But Thursday, come prepared for presentations.